Alrighty, we are starting recording now. Welcome everyone to the COT3100, that is Applications for Discrete Data Structures review for exam 4. If you're here in person, well, welcome. If you're here on Zoom, welcome. If you're unable to be here and you're perhaps watching like an uploaded YouTube recording of this later on, also welcome. During this review, we are going to be trying to go over everything that I think will be on the exam for exam 4 for the class. With that being said, I do have my usual disclaimers. 1, no, I'm not a TA for this class. 2, no, I'm not the professor for this class. Therefore, there might be things in the presentation that could technically be wrong. If you notice something that's wrong in the presentation, please just point it out. The goal for these review sessions is not to spread misinformation. It's for everybody to basically have a group study, and hopefully we can get the exam averages higher by reviewing all the content. With that being said, I guess I'm just going to get started. So hopefully everybody can see the PowerPoint, right? Hopefully, yeah, okay, cool. I'm just going to assume everyone can. So let me get up the, hold up. This Zoom is blocking me, guys. All right, there we go. I got it. We're good. All right, so we got the main topics for exam 4. Previous stuff, algorithms, and time complexity. Oh, wait, I gotta mute everyone. No, I cannot be getting a phone call right now. Ain't no way. All right, let's see. We got algorithms and time complexity. I'm not going to be going over today. That is stuff from previous exams. There is another review on that stuff that is recorded on YouTube if you would like to rewatch that content. That can show up on the exams, just for heads up. The algorithm stuff, that's like knowing big O time and knowing how to, write pseudocode and all that stuff. There's also the new stuff on this exam is counting, looking at combinations and permutations and all that stuff. Probability and graphs. So that's the stuff that we're going to focus on reviewing today. So first part of counting, we got some rules to go over. Some of these are really basic, some of these are not quite as basic, but let's start with the rule of sums. Okay, it's really, really simple actually. Let's say you had 5. Come on, right? Okay, so you had. Hold on. Let's say you had 5 blue books, right? In this scenario. And you had 3 green books, right? Okay, so the division of sums, what that's saying is if we wanted to select one random book from both of these groups, how many different options of books could we have? Well, it's as simple as just saying 5 plus 3 is equal to 8 total options of books. Okay. The rule of products, on the other hand, let's say we wanted to say if we wanted to select 1 blue book and 1 green book, how many different combinations of books are there? So in order to do this, it's exactly what it sounds like. Once again, the rule of products, it kind of implies that you're going to use multiplication. Think about it. For every single blue book, there's going to be 3 options of green books. And we have 5 options of blue books and, like I said, 3 options of green books. So essentially what you're going to be doing is you're just going to do 5 times 3 is equal to 15 combinations, right? And we have something that's a little bit more complicated. Now, I think the general purpose of the division rule is when you're looking at something and maybe you're splitting into groups, but maybe the order doesn't really matter in those groups. So you have some form of overlap. So I know that when Dobbins was going over this, he gave an example. He said that let's say you have 10 people, right? And you're trying to seat 10 people at a circular table of 4. And it's asking how many different groups of people can be made. Now, when it says different groups of people, what this means is that, let's say person A, B, C, and D were sitting together. It doesn't really matter their orientation at the table. No matter their orientation, it's still the same people at the table. Therefore, you could have them circle essentially, and even when they rotate, it's still the same exact people. So there's 4 different ways to make the same group of people at a circular 4-person table. So in order to find out, so once again, let's say we had 10 people and we're trying to see how many different combinations of 4 different people at the table we can make? Well, first we're going to have 10 people. So we're going to have 10 people. And then after that, we're going to have 9 more people left. So then we're going to have 9 more combinations, right? And then after that, we're going to have 8 more people left. So then we're going to have 8 more combinations possible. And then after that, we're going to have 7 more people left, right? Do you guys kind of understand, like, this is like how many total different ways we can arrange the people into this problem? But like I mentioned earlier, like I explained, when we have this table, we know that there are 4 different ways for each group. So we're going to have to end up dividing by 4. Now, if I do this math real quick, we get 10 times 9 times 8 times 7, we get 5,040 divided by 4, which is 1260, which I believe is the same answer that you get in the lecture slides on Dobbin's slides. So keep that in mind. Let's see. I'm going to go to the Zoom real quick. I'm going to participants. Beautiful. There you go. I've just muted everyone. That way we have no sounds. So we're going to move on now. All right. So now we have part 2. We have the inclusion-exclusion principle. Okay. This one is pretty simple. If you have 2 conditions, right, or you have 2 items, right, and you wanted to basically find the total number of items that have either one or the other condition, you're going to add the total number of items from those 2 conditions and then subtract the overlap. The reason you're subtracting the overlap is so that you are not accidentally adding objects twice. So for example, let's say we had a deck of 52 cards, right? 52 card deck. And we wanted to find out how many cards there are that are either red or what's a good card number? I don't know. Hearts? Well, red or hearts, that would just be all the red cards. Wait, no, a number. Okay, let's make this spicy. Let's do like red cards or their face cards, okay? Face cards being king, jack, queen, not ace. So let's say, so what do we do here? How many red cards are there total? Come on, guys. We gotta, hopefully we have some poker fanatics in the here. 10? All right. So for you, those of you who have not played cards, come on, guys. Like, you must be losers. But anyways, essentially, in a deck of cards, you have half of them are red cards and half of them are black cards, right? So you have 26 red cards. Now, for the face cards, like I said, there are jack, queen, and king, right? So each jack, queen, and king is going to have 12 cards, right? Well, or rather 4 cards each times the 3 suits. That's going to be a total of 12 cards, okay? However, of the jack, kings, and queens, we then need to subtract the overlap. Now, the overlap in this case would be the number of cards that are both red and are face cards. So there are a total of 6 cards that are both red and face cards, aka, we have the jack of hearts, the jack of diamonds, the queen of hearts, the queen of diamonds, and the king of hearts, and the king of diamonds. So we're going to subtract that overlap from here, and then we would get a total of 26 plus 12 minus 6 is 6, so 26 plus 6 is 32, right? That's how we would do something like that. Final answer. And then after that, another principle we have for this counting thing is, yeah. What do you mean? Oh, why do we subtract 6?
No, why is it 6? I've never played cards.
Oh, okay. So basically, when you play cards, right? When you have a deck of 52 cards, right?
Yeah.
So a standard deck has 52 cards. How this works is half the cards are red and half the cards are black, right? Now, how the 52 cards works is you have the numbers 1 through 10, 1 being ace. You have 1 through 10, and then you have queen, jack, king. So notice that there's 13 total suits or numbers or whatever you want to call them. 32 total or 13 total sets of 4 cards. Right, there's 2 of each red, because there's gonna be hearts and diamonds, and by the way, you might need to know this for the exam, just putting that out there. Just so you know, like, cards is like a really common thing, so like, they might get this stuff on the exam. But yeah, basically, so you'll have half the cards are red and half the cards are black, because there's hearts and diamonds, which are red, and then there's spades and, let's see, what is the other, spades and clovers? Yeah, spades and clovers, which are black, right? So basically, if you haven't looked up the, how a distribution of cards looks, you might want to look this up, just so you know. Like, it actually might be, it might be somewhat important. Hold up, somebody was trying to unmute themselves. Did somebody need to talk or something? Because I saw somebody wanted to unmute themselves, but was somebody saying something? I'm not sure. Okay, anyways, so now we have this thing called the pigeonhole principle. Okay, now the basis behind this is, let's say you had like a ton of pigeon coops, right? And let's say you had a certain number of pigeons. Okay, if you had 7 pigeon coops and 8 pigeons, and you wanted to put all 8 pigeons into the set of pigeon coops, what that essentially means is that no matter what, you're going to have at least 2 pigeons in at least 1 pigeon coop, because you could put 7 pigeons in a pigeon coop, and or you could put 1 pigeon in each of 7 pigeon coops, but then you're still going to have 1 left over no matter what that you're going to have to shove in with another pigeon. Now, that doesn't mean that there's like an upper bound, right? Like, for example, if we have 8 pigeons and 7 pigeon coops, that doesn't mean there's 2 pigeons in every coop. And quite frankly, it doesn't mean that there's even 1 pigeon in every coop. It just means that there are at least 2 pigeons in at least 1 coop. Like, we could take all 8 pigeons theoretically and shove them into 1 coop. And then we have 8 pigeons in 1 coop. And in the other 6 coops, we have 0, right? But the point here is that basically you have at least 1, or you have at least 1 coop with at least 2 pigeons. Now that sounds really complicated, but when you look at this formula right here that's written, the ceiling of n over k, it makes more sense. N being the number of objects, and k being the number of boxes or whatever storage containers, whatever you want to call them. Let's see. So I'm going to go ahead. I think I had some questions written down that I just thought we might as well go through, because I think going over some practice problems would be good. Yeah, I do. So these were some questions that I wrote, but we're just going to go over them. So let me try to move this up a little bit. That way I can write this out. So let's say you had, I wrote these questions based on, we were having a certain number of people moving into a neighborhood. Okay. So we have 41 homes. First one says 41 homes in the neighborhood. And we have 378 residents, okay? And now we have a question that says, what is the minimum number of people in the largest household possible, okay? So we're going to use this little formula right here. That is basically the definition of the pigeonhole principle. So we're going to say 378 divided by, we know we have 41 containers, and we have 378 people, which is, people are objects, guys, come on, we're programmers. And we're going to floor that function. So now if I do that real quick here, 378 divided by 41. So when you do that calculation, you get 9.2, but remember, not floor, ceiling. Remember, we're ceilinging that function, right? So therefore, because we're putting the ceiling, that goes from 9.2 to 10. Hopefully you remember that from, I believe, is that exam 2 or exam 3? I have no clue, something like that. But so there's going to be at least 1 household in this neighborhood with 10 people, basically. There could be a household, at least 1 household with at least 10 people. We could have a household with like 15 people, and in which case, then all the rest of the houses could have less than 10 people or something along those lines. But just keep in mind that at least 1 household will have at least 10 people in this neighborhood. Now, I have another question written down here. If we have 63 homes, how many people must be present to guarantee a home with at least 6 people? So this is saying we have 63 homes. How to guarantee a home with 6 people, right? So what this is saying is how many residents would we theoretically have to have in order to guarantee that there are at least 6 people in at least one home. Now, in order to do this, we're going to actually manipulate this function here, this ceiling function. And really what it is you're going to take the 63 homes, right? And you're going to multiply it by, essentially, we have 6 plus people. You're going to take that and you're going to subtract 1. So you're going to do 63 plus times 5, right? And then you're going to add 1. Now, let me show you what happens when I do this. So when we do this, we get 316, right? Now notice if I go back, and that is our final answer, actually. Notice when I go back to this formula and I put in 316 over our K is going to be 63 homes, and I do the floor, I get just probably barely I get 5.01. So I just get barely above 5, which once again, if we seal it, we're going to get 6. So that's the lowest value that would guarantee that there is at least 6 people in at least one home. Hopefully that kind of makes sense to any of those who were struggling with this principle. So we're going to move on. Counting part 3, permutations and combinations. Now I did notice that when I was looking through Dobbin's lectures, I'm like 99% sure, I obviously went and Googled it and everything. There was a typo in those. So I'm pretty sure, 99% sure this is correct though. Basically, when you're doing permutations and combinations, N is going to be your number of objects, and R is going to be the number of objects being selected, aka the number of containers. Once again, on Dobbin's slide, I noticed that it was actually swapped, but that just wouldn't really make sense. So anyways, with permutations, we're saying we're going to find the number of combinations, but basically the order matters. So for example, let's say we were doing something with letters and we had A, B, C, D, then the combination A, C, B, D and A, B, C, D would be 2 different things. There would be 2 different combinations. With the combination down there, what we're basically saying is that A, B, C, D and A, B, D, C, or just a different assortment of the same letters, you're saying that doesn't matter, and those are still counted as one thing together. So that is why for combinations, you'll notice we have this random little factor down here that's making it less, because you're going to have less combinations, because once again, those combinations are considered the same thing, whereas for the permutations, they aren't considered the same thing.
Permutations are for order.
Permutations are if order
matters.
If order matters, yes. Combinations are if order does not matter, and therefore, because the order doesn't matter, you have less total groups of objects, basically, that can be made. You'll have to read the problem in order to understand which one to use. So for example, if you're I know that some in the RE, it was talking about baseball teams, and it's how many different combinations of baseball players can you make? Well, think about that for a second, right? It wasn't saying that their position on the field mattered or anything. So because the position on the field doesn't matter, it's just asking how many different ways can different players be chosen. What that means is that the order is not really mattering, so you're going to end up using combinations. Now, if it said how many different ways can players play different positions, and all of a sudden, who's at bat matters and who's in the outfield and all that stuff, then all of a sudden you're going to be using the permutations. There's going to be a lot more possibilities. Is that my mic or is that thunder? Ah, that is really loud thunder, guys. That's crazy. Okay, I was making sure I didn't bump my mic, and I'm slightly killing everyone's ears right now. Anybody got an umbrella here? All right, so I went back. Wait, did I? Oh, no, we got probability part one now. Cool. Unless do you guys want me to just go over one of these? I'll just go over. All right, sweet. Okay, so let's say we had a permutation. So you'll notice that the n value will typically be greater than the r value, because if you have like 4 objects and you're putting them into like 3 containers, that kind of makes sense. If you have like 3 objects and you're putting them into 4 containers, that doesn't really make as much sense. Also, the fact that you have to do n minus r in the formula down here, and we haven't really gone over like how to do negative factorials, so that just also wouldn't make sense. So once again, your n value is typically going to be larger than your r value. But so let's say we had like p of 3, 4. Well, it would be as simple as 3 factorial over. Oh wait, hold up, I take that back. I gotta do 4, 3. What am I doing? I literally just explained. I just explained how the n should be higher. But anyways, so we would do n 4 factorial, and it would be 4 minus 3 factorial. Now this would be equal to 4 factorial over 1 factorial, which is equal to 4 factorial, which I believe is equal to like 24, right? Yeah, something like that. Okay. Does that kind of make sense to you guys?
Yeah, can you give like a word problem?
A word problem? All right, let me think about this. So for this, it would be like, let's say, once again, let's go back to our baseball example, okay? It would be like, let's say you have 4 baseball players, right? And for the permutations, it would say how many combination, well, I don't want to use the word combinations in the permutations example, but let's say you had 4 baseball players, right? And you had to select 3 players to play in the game, right? How many different ways could you select players? Now, for this combinations example, if it said, no, I take that back. I take it back. It would say, it would be for the permutations, right? Let's say you had 4 players and you had to choose 3 right? It would be how many ways can you select different positions? So let's say you had 3 positions, right? Right.
So positions are like.
Yeah, so that way positions matter. Like, because if you're looking, once again, if you're like looking like who's at bat, who's at first base, who's at second base, those would be different things. Yeah. Oh, that was your answer? Yeah. If you're looking at who's at bat and everything, right? That would be the permutations. Once again, for the same exact example, if you said you have 4 baseball players and we just want to see how many teams of 3 we can make, that way the positions don't really matter, and it's just the same. Like if we have person A, B, and C, it's the same thing as person B, C, and A, right? Then that's when we would use combinations. So a combination of 4 and 3 would basically look like this. We're going to have the combination is going to be 4 over. We're still going to have this 4 minus 3 factorial, which is 1 factorial, but then also we're going to have 3 factorial here. So it's going to be 4 over 3 times 1. Now this is 1, so it's going to be 4 factorial over 3 factorial. Now that is going to be, keep in mind, 4 factorial is 4 times 3 factorial over 3 factorial. These cancel, and yes, you get 4. There you go. Hopefully that somewhat makes sense. Does everyone understand? Okay, cool. Awesome. I got some thumbs up, so I'm going to move on. If you have any more questions, feel free to come to me after the review session. So now we have inclusion, exclusion again, but instead, we have it for probabilities. So this is another inclusion, exclusion. What this is really saying is the probability of one event or another event is equal to the probability of the 2 events added, or minus the probability of the 2 events being together. So I made this problem here. This is actually really just a more general inclusion exclusion problem, but I thought it was kind of fun one. So we have 88 keys on a standard piano. Of these keys, 36 are black keys and 52 are white keys. How many keys are either on the left half of the piano or are black, assuming that the piano is evenly distributed, basically. So yes, so let's see. So first to do this, we're going to do either on the left half. So we have 88 keys. So that means that on the left half, there would be 44 keys, right? A total, because it's just 88 divided by 2. Plus, we have 36 keys that are black, okay? So we're going to add the 36. But then we're going to have to subtract what amount of keys are both black and on the left, right? Which in this case would be just the 36. Once again, we're assuming it's just evenly distributed. So 36 black keys divided by 2 would be all the ones on the left. So we're going to have to subtract the 18, right? And if I do that math real quick, we're just going to get 44 plus 36 minus 18. We get 62 keys. Now, let's say this problem, instead of saying this question, let's say it were to say, what is the probability, right? Instead of just asking how many. So we're going to do 44 over 88 plus, it would be 36 over 88 minus 18 over 88. Yes, I'm doing this 2 ways to show a proof. That's why. So essentially, we would have the probability would be 44 over 88 plus 36 over 88 minus 18 over 88, which is going to once again get us 62 over 88. Now notice that this probability here matches this right here. And that does go to like one of the basic rules of probability, which is that the probability is equal to, I believe, the number of elements in a set over the number of like total basically members in that set, something along those lines, the number. So do you guys see how that does kind of work out? Hopefully you can see this is like inclusion, exclusion part 1, the part that we went over earlier without the probabilities, just with the counting. And so I'm going to write counting right here just so anybody looking at this later can understand what's happening. And then this is with probabilities. Hopefully, if you've taken like a stats class, this is more like review than it is new content. I will say that, especially in the REs, some of these probability examples are like super duper abnormally complicated for no reason. And I'm hoping that when we get to the exam, there's nothing that's like that complicated. All right, so now we have probability part 2. Let's see. First of all, we need to know what a uniform distribution is. That is essentially where you have multiple options, but whichever option you choose is like just the probability is just like 1 over n. So for example, let's say you were like rolling a dice, and the dice, assuming it's like unweighted and all that, it's not rigged. Like the probability to get a 1 is a 1 out of 6. Well, assuming it's a normal 6-sided dice, but probability to get a 1 is a 1 out of 6. The probability to get a 2 is also a 1 out of 6. There are 6 total options. The probability to get each option is just 1 over n, 1 over 6. So make sure you know what that is. Just in the case, I don't know, if we have a question that's like, is this a uniform distribution? And it gives you something like that. Or we could get a question like, give an example of a uniform distribution, something along those lines. Okay. We also have conditional probability. And I have a little graph that I drew earlier that I wanted to share with you guys for an example question for this. So the probability of E given F, E and F both being 2 separate events, is the probability of E and F over, or rather the cardinality of objects of E and F over just the cardinality of F. Okay, so let's say I had quite a few markers. Okay, we have markers. Okay. Now, when we have markers, you guys have done like my expo markers, right? There's a few different ways you can have different types of markers. Okay. One way you can have different markers is, they can differ by color. You might have blue markers, you might have red markers, etc. Another way that they might differ is you might have markers that are thin, you might have markers that are thicker. Basically, the markers like the end of the tip. I don't know what you call that, but the tip might be finer or thicker, right? So we're going to have blue markers and red markers. And we're going to have normal markers, and we're going to have thin markers, right? Okay. We're going to have this wonderful table here. And then we're going to have like total, etc. So I'm going to draw this. There we go. So I have some numbers already here added up. So let's say we have 25 normal blues. We have 20 thin blues. Now this would give us 45 total blues, right? And let's say we have 15 normal reds and 17 thin reds, right? And this would give us a total of 32 total reds. Now, if we look at the normal markers, that means we have a total of 25 plus 15. That's the same thing as 30 plus 10, which is 40. And if we look at the thin, we have 20 plus 17, which is 37. So now notice that the totals should both add up to the same thing, which is 77 total markers, right? That makes sense, everyone. I'm just like assigning random values just for the example's sake. Let's say we had a question and it was like something like, how many blue markers do we have given that we know that it's a thin marker, okay? So what we're gonna do, right, is we're gonna take the number of basically both blue. So we're gonna say blue. Also, this is how it's usually written, by the way. It's usually blue given thin. And maybe you'll have like a probability or something like that, okay? This little pipeline right here means given, okay? So blue given thin, that's going to basically say, we're going to take the probability here. We're going to say, what is blue and, or how many markers are both blue and thin? So we're going to go to this graph. We're going to say blue is right here, thin is right here. So we have 20 total markers that are blue and thin, right? But now we're going to go and we're going to say, how many total markers are just thin, right? So if we go to thin, we go to the total column, we get 20 over 37, which I guess the probability would then be, if I do the math real quick, we get 0.54, which is equal to about 54%, right? So does that make sense for how to do conditional probability? Just making sure everyone's kind of down on that. All right, awesome. All right, now we have probability part 3 of Bernoulli trials. There is a very long proof, well, not super long, it's like 6 lines. There's a 6-line proof in the PowerPoint slides of how to prove Bernoulli trials here. I don't have them memorized off the top of my head, but I would highly recommend if you're gonna like copy down some proofs on your cheat sheet, like this is probably one of the proofs you might want to copy. It's once again, it's in the lecture slides. So I would go ahead and potentially copy that. Basically what a Bernoulli trial is saying is you have an event occur and that event has 2 possibilities. It can either succeed or it can fail. Now notice that if there's only these 2 possibilities and its probability of success is 25%, then its probability of failure is just going to be 1 minus that 25%, 1 minus 0.25, 0.75 or 75%, right? So a lot of times it's like the probability of failure is going to be 1 minus the probability of success, right? That's a common formula that you're given. Once again, I would have this on your formula sheet, or you can just memorize it. It's a pretty simple formula. The formula that I definitely recommend putting on your formula sheet, okay, is this formula right here. This is the probability of something that you know, how many successes in n number of trials. The probability of, once again, the probability of, I guess it's written right there, but the probability of k successes in n trials. So I'm going to run us through an example of this, okay? I wrote down a good example. So let's see, what is the probability I wrote probability wrong, hold up. Probability if we flip 10 coins, that we get 7 heads, right? So once again, this is just as simple as we're taking some coins, we're flipping them, and we're trying to find the probability that we get 7 out of the 10 as heads. So what I'm going to say is that our probability of success, our P, well, when we flip a coin, what's the probabilities? Assuming that it's not weighted or anything. 1/2, right? 0.5. So we're going to say the probability of success is going to be 0.5, and the probability of failure is equal to also 0.5, right? Because it's 1 minus that 0.5. And now we have the fancy combinations formula in there too. And we have, keep in mind that this is the probability. K is the number of successes we want. So our K is going to be 7 successes. And our N, we are flipping it 10 times, so it's going to be 10. So now if we plug it in this formula, we're going to get C. And once again, this is the combinations that we talked about earlier. So we're going to get C. We have an N of 10, a K of 7, and we're going to go 0.5, 0.50 times the K is 7 times 0.50, and N minus K is going to be 10 minus 7. Now, if we do this combination thing, we're going to get 10 factorial over. Remember that we need to, on this side, we can have 10 minus 7 factorial. And right here, we're going to have, I believe in the formula for combinations, we have the R factorial, right? So that is going to give us 7 factorial right here. And then right here, we're going to have the same 0.5 to the 7th power. And that's going to be 0.50 to the 3rd power. Now, if somebody, does anybody have a graphing calculator on them or no? Oh, I can get one out right here. I will calculate this real quick. And let's see. So if we take this fancy formula here and we calculate 10 factorial divided by, now 10 minus 7 is going to be 3 factorial, right? So we're going to do divided by 3 factorial divided by 7 factorial. And then we're going to do times 0.5 to the 7th times 0.5 to the 3rd. We get 0.1171. So that's basically 0.1171, which is equal to 11.71%.
The combination
So the C basically turns into
combination is C10, and then you just combine the X with the 0.5 to the power of 10.
Yeah, are you saying could you just like add these exponents? Yeah, so that could be to the 10th, yes. Basic math rules still do indeed apply. If anybody wants to like Google what's the probability of getting 7 heads if you flip 10 coins, and see if you get something along the lines of 11 point, like just Google it and see if it tells you like 11, 12% or something, that should be the answer. All right, cool, yeah. All right, so now we finally are moving into the final, what time is it, by the way? Hold on. 7:45. Okay, we've been here for 45 minutes. We're actually kind of on time. Usually these things run super far over time. True. But anyways, so we're 2/3 done and we're 45 minutes in. Okay. So finally we have what I think is honestly like the funnest unit. Most fun, funnest, funner? I don't know. What I think is the most fun unit in this group, to be honest. Like, I don't know if this unit is like kind of abstract, but I don't know, like it's kind of interesting to me. But the graph's part of this unit. So anyways, we got a simple graph. What is a simple graph? So basically, this is the example we get in the slides. Notice for this example, it's very, very, very simple, right? And these are also only for undirected graphs, just so you guys know. Let me write that here. Anyways, so we have a simple graph. There are not multiple connections happening between two of the same pair of nodes, and there are also no loops, okay? So we have a multi-graph where we have multiple edges. What that means is that we might have a graph like this. And note that all of these dots are nodes or vertex. They're vertices, singular one being a vertex. And these lines are called edges, okay? They're connecting two things. So with the multi-graph, we might have something like this. And then we also might have maybe a pair of vertices that has two. Okay, so we have multiple edges on each. Notice that for this, for each, once again, for each vertex or vertice pair, there's only one. And then we have a pseudograph, which essentially adds in loops. So we can have a pseudograph that looks something like this, right? We're gonna do 1, 2, 3, 4. Fancy. And then let's say we had like one that's like this. Okay, and that would be something with a loop. So that would be a pseudograph. Now, if we move on, we have all these different relations. So we have adjacency. What adjacency is saying is it's two vertices are attached by an edge. We have incidence, which is basically saying that an edge, it's the exact opposite. It's an edge attaches to a vertice or a vertex. We also have the degree. The degree is the number of edges coming off of a vertex. Now, in order to get the degree of an entire graph, you add up all of the degrees of the individual vertexes, I believe. So what this means is, and I believe there is a proof of this somewhere, but what essentially this means is that the degree of an entire graph comes out to 2 times the number of edges, because think about it, for every single edge, there's going to be like 2 vertexes like on there, right? Or something. Yeah. So, or rather, each edge has 2 sides. It's going to be connected to a vertex, right? So once again, so the degree for an entire graph, you add up all of the degrees of each individual vertex. You also have the neighborhood, which is going to be the set of vertices adjacent to a vertex. So it's basically if a vertex is connected to another vertex by an edge, then those 2 and thus they're adjacent. Thus, if we had like vertex 1 and vertex 2 would be in the neighborhood of vertex 1. Okay. Let me think. How do we continue? I want to go over these a little bit more. So basically, I'm just going to say, actually, I take that back, because here's the thing. We're going to go over this really in depth with the matrices and lists in a second. So I'm just going to move on, actually. So now we have all of the types of graphs. There are these 6 types, and then there's a couple of special types that are like kind of based off of these types. But anyways, we have a complete graph. So you're going to notice that there's these ends at the bottom. The ends have to do with how many vertices there are in the graph. Unless we get to a wheel, which is actually going to be like, even though there's an end, there's going to actually be one more added vertex because there's one in the middle. But if we had, let's say we had like a K of 5, right? We're going to draw 5 vertices. And this one is the complete graph. This means that every single vertice attaches to every single, or is adjacent to every single vertice. So, or vertex, whatever, plural, single. So I'm going to, oh no, my drawing of the star was not very good. But basically you can draw a star to connect these. And then after that, you also have to do this. So now they're all connected to each other, yes. Okay. I promise I'm not drawing like a pentagram. Okay. Let's see. Then we have a cycle. Now a cycle is kind of part of a complete graph, but not complete. Essentially what we're doing, let's say we had a C of 5, right? We're going to draw these same 5 vertices. A cycle only includes the outer edges. Okay, sorry, my drawings are horrendous, but it is what it is. We're trying. Now, a wheel, on the other hand, we add one in the middle. And it's basically the cycle, but you add a vertex in the middle, or a vertex in the middle, and then you basically connect all the outer vertices to that inner vertex. So we're going to have, once again, the same 5. If we did like a wheel of 5, we have the same 5, but then we're going to have one in the middle. We're going to connect all the outer ones. And that would be a wheel right there. You can see it kind of looks like a wheel, right? Hopefully. And the cycle kind of looks like it's going around, and the complete is just everything. So next we have cubes. So I'm going to draw what will be a cube of 3, right? Now, when you look at cubes, this is basically how many dimensions it looks like it has, okay? Kind of, essentially. So how do we draw a 3-dimensional cube? Well, that's a good question. It's 1, 2, 3, 4. Make these bigger. And then after that, it would be like 1, 2, 3, 4. something like that, right? So that's, once again, that is a Q3, that is a three-dimensional cube. My drawing is horrendous, but it's okay, trust. So then finally, we have this thing, well, not finally, but we also have this thing called a hypercube that you do need to know exists. Also, when you look at these cubes, a lot of times they take them. Notice that as you go up a dimension, right, it goes up by a factor of 4 for the number of vertices. So like before this, so notice that we have 8 here, or rather it goes up by a factor of 2, I take it back. It goes up by a factor of 2 for the number of vertices. So what that means is that you can actually represent each vertex in a cube by some form of binary. So, for example, for a cube, since there's 8 vertices, like you could like label this as like 0, 0, 0, and you could label this as like 0, 0, 1, 0, 1, 1, 0, 1, 0. Hold up, why did I do 0? Oh, wait, yeah, that works. What? Yeah, so the vertices, yeah. So for example, the vertices would be 2 to the power of n. So like, for example, if this is 3, we have 2 to the power of 3 is going to be 8, right? Now for this hypercube, right? We're going to have 2 to the power of 4 vertices. So we're going to have 16 total vertices. So how does that make any sense? So basically what we're going to do, we're going to draw 2 cubes, right? So first it's going to be like this, like this, and like this, and like this. Okay, and then we're going to go like right here. We're going to draw like this. We're going to draw like this, and like this, and like this. We're going to go. Okay. Then after that, we're going to draw this and this, this and this, and then we have 1 cube, right? But once again, think about this. We have to have 16 vertices, right? So how do we do that? Well, we're going to draw another cube, okay? And then basically, so let's draw another cube. So we have this, and this, and this, and this, right? Okay. And then we have this, and this, and this, and this. Then we're going to go like this. Okay. And then after that, so now we have 2 cubes, right? And now what we're going to do is we're just going to connect each vertex of each cube basically to its corresponding vertex of the other cube. So it's going to be like, and then this would go here, and then this would go here, and then this would go here, okay? And then this would go here, and this would go here. Some of them are kind of overlapping because I drew them so close. Let's go here, and this would go here. So then, I don't know if you can kind of tell, but have you guys ever seen like the GIF of the illusion? There's like an illusion of, oh, this is what the 4-dimensional looks like. If you look it up on your phone, you can look up like 4-dimensional GIF, and you'll see one of these things, and it's just like rotating around, and that's a hypercube. It's like a cube. Well, it's making it so that your dimensions, instead of being like 2-dimensional dimensions in 3D, all of a sudden are like 3D dimensions, and you have multiple of them connected essentially. So keep that in mind. You might need to know what a hypercube is for the exam. And you have bipartite graphs. Bipartite graphs are basically where you have 2 values here now, notice. You have an M and an M. And essentially, let's say we have a K of like, I don't know, let's say 3 and 2, okay? We're going to take 3 and we're going to draw 3 nodes here. And then we're going to draw another one and we're going to do 2 here. And a bipartite graph. Is that my mic? Yeah, I think that was.
That was my fault. Sorry. Oh.
Oh, I need it. Let's see. Hold on.
I accidentally unmuted myself.
I don't know why, because earlier, like I said no to permissions to unmute, but there you go. Everyone's muted again. Anyways, so yeah, we have this bipartite graph, and for this graph, I might just have like some connections, right? Oh no, what have I done? I need to click pen mode again. We might have some connections like this. Okay, that's a bipartite graph. Now, we have this special thing called a complete bipartite graph. Now, just a normal complete bipartite. Also, I don't even know if I'm pronouncing this correctly, but it's okay. Yeah, I got you. There you go. Yeah. Yeah. Yes. Yes, the bipart, for those of you who didn't hear what Vedant just said, he was saying it looks like a function and you could say like it's onto or whatever. Yes. Okay, so for the wheel, specifically for the wheel, because you have that node in the middle, it's actually like the number that you have is going to be one less than the actual number of vertices you have. So like this is a real 5 because it goes by these 5, even though it actually has 6. You're right. Yeah. I can check that just to make sure. Who was copy? Yeah, let me know when you're done. Yeah. I'll check that to make sure though.
Oh, no, I checked it on our technical, that's correct.
Okay, cool. Thanks. Yeah, that's what I thought. So anyways, we have a complete bipartite graph here. So basically what that means is let's draw our like K. What did I do over here? I did a K32. So let's draw our K32 here, right? Wait, no, what have I done? Okay. We draw our K32. What this is saying is that basically for every single vertex is connected in this graph. So we're gonna have 1, 2, 1, 2, and 1, 2. Notice that the complete bipartite, it kind of looks like a basketball hoop. I don't know, basketball net. A lot of times, if we like turned it. But anyways, for this special case, this star, it's basically a complete bipartite graph, but the first number is always 1. So this means is that if we had like a star, say we had a star of 5, right? This would be equal to a complete bipartite graph with 1, 5, right? So now what this would look like is we basically have 1 here, and then we had 5 around it. 1, 2, 3, 4, 5, and then basically just goes like that. Notice this also kind of looks somewhat, it looks somewhat like the wheel, right? But the difference between this and the wheel is that this does not include the cycle. Remember, the wheel is kind of the cycle and the star. Notice there's the cycle and the star there. The star is just the wheel without the cycle part, and the cycle is just the wheel without the star part. So hopefully you can start making those connections, and that makes a bit of sense. So we have subgraphs. Subgraphs, what this is basically saying, you guys remember this symbol from like 2 units ago? What does this symbol mean? Just a subset. So proper subset would be without the equal sign, right? This has the equal sign. So basically what this is saying though, it's very similar to a less than or equal to sign. So if we had one graph, right? We had a graph like this. And let's say we have these 4 nodes in the corners, right? And we wanted to say, is this a proper, or is this a subgraph of this graph? That's such a bad drawing. If we wanted to say this, what would you guys think? Is this a subgraph? Is the left a subgraph of the right? Yes. Yes, because notice how basically this graph is basically included in this graph, right? So that's a yes. Now, if we said the other way around, right? We said the other way around. What would the answer be there? No, good. So that is not the case.
Okay, so whatever's on the left needs to have.
It needs to basically be part of what's on the right. Does that make sense? Because once again, it's a less than or equal to sign. And basically for something to be a subgraph, it means that every single part of that graph is included in the other graph, the graph you're comparing it to. So we have our cycle, right? Let's say we have our cycle like this. Would that be would that be a subgraph of our wheel? That was a terrible wheel drawing, but it's okay. Is that, would you guys say those are subgraphs? Or would you say one is the subgraph of the other? Yes, that would be. Think about it, because every single part of this graph is included in that graph, right? So that would be yes. Does that hopefully make sense after looking through some examples? All right. Cool. All right, now this part's going to take quite a while, unfortunately. But it's not that bad. Suppose we have adjacency, and I want to go over both lists and matrices, and then I also want to go over both undirected and directed, right? So let me get up some notes here, right? Hold up. I want to make sure that I get all these matrices down spot.
Directed needs to have vectors, right?
So directed, yes. So directed doesn't mean have a direction. So like if we have directed, when we go over directed, I'll just like add some fancy directions. That way we can actually do it properly. But anyways, what I wanted to check something real quick. Hold up. I just thought of an interesting scenario. I want to see. Okay, cool. I was just checking something for my own knowledge. But anyways, so we have an undirected graph and we have this A, B, D, E, A, B, C, D, E, right? I don't know why I put them out of order, but it doesn't really matter. So in order to say, to make a list, right? I'm going to list out all of the vertices, and we're going to first start with an adjacency list with the undirected. So I'm going to list A, B, C, D, E, and now we're going to have an adjacency list, right? So in order to do this, which vertices are adjacent to A? It's the ones that are connected, right? C and E, you guys agree with that? See how it's like C, well, C and E, right? So C, E. And then we have B. Which ones are these? D and E. And we have C, which one are these? A and D. And then D, which ones are these? And then E finally is going to be A and B, right? So do you guys see how to make an adjacency list? Are you guys confident that if you were given a different graph from this graph, you could make one? Because I can like almost 100% guarantee that there's going to be like an adjacency list or matrices in like our matrix in our exam. Like I'm like 100% confident in this. So yeah, if you don't know how to do this, then I would highly recommend rewatching this and figuring out how to do it. But basically, once again, what I'm really just doing is just looking A is connected to E, so we put E there, and A is connected to C, so we put C there, right? It's not that bad. Now we're going to make this a matrices, okay? In order to do that, basically, we're going to list all of them right here, A, B, C, D, E. And then we're going to list all of them up here, okay? A, B, C, D, E. And make our little matrices. Now what we're going to do is basically say, okay, is A connecting to itself? No. In order to connect to itself, we would have to have like a loop or something, right? It doesn't. So because A is not connecting to itself, we're going to put a 0 here. Is A connecting to B? No. Is A connecting to C? Yes. We're going to put a 1. 1 is true. 0 is false, yes. So is A connecting to D? No. Is A connecting to E? Yes. Okay, do you guys see how that's kind of working? So then let's go through the same thing. Is B connecting to A? No. Is B connecting to B? No. Is B connecting to C? No. Is B connecting to D? Yes. Is B connecting to E? Yes. Okay. Next up we have, is C connecting to A? Yes, it is. Is C connecting to B? No. C connecting to C? No. C connecting to D? Yes. And C connecting to E? No. Okay, and then after that we have D. So notice that D is just C and B, right? So I'm just going to go to C and B and write ones, and then everywhere else is zeros. And then for E, we have A and B, so those two are going to be ones, and then everywhere else zeros. So does that also kind of make sense to you guys? Now notice if there are no loops, there are never any vertices that are connecting to themselves. So like that's why we have this like diagonal zeros, because there's no loops or anything in this graph. Now, let's say we had a directed graph, okay? Let's say I'm going to just draw a graph. So we had A, B, C, and we'll just say A, B, C, okay? What a directed graph will look like, we're going to have arrows. Okay, and screw it. Why don't I just like add a little loop on to make this fun? Okay. So essentially for this adjacency list, when you do a directed, you're going to be looking at the out degree for this to work. What that means is that when we're looking at what's adjacent, we're looking at what is starting at your point and going to another in order for it to be adjacent to something else. So when we do our adjacency list, we're going to have A. Now, what is A adjacent to? Any guesses? Right, A and B. It's adjacent to itself because I put that loop there, so it's going out and back to itself, and it's also adjacent to B, right? Because it's going out into B. Now, if I put B here, what is that adjacent to? C. If I put C here, what is that adjacent to? A. Okay, cool. So now we're going to make our matrix for this. And in the same fashion as before, I'm going to write A. We only have 3 now, so it's just A, B, C, A, B, C. So is A adjacent to A? We said yes. Is A adjacent to B? We said yes. Is A adjacent to C? No. Because C, even though the two are connected, right? Notice that C is pointing at A. It's not being pointed to from A, okay? Now we have B. B is the only thing that it's pointing to is C. So we're just going to do 0, 0, C. And then for C, the only thing it's pointing to is A. So it's going to be 1, 0, 0. So hopefully does it, yes. Yes, yes. What he was saying is for undirected, it's always symmetric. The only thing that you might not have that like looks symmetric, but it's still technically symmetric, is if you add a loop in an undirected graph, like your zeros and one, like this might not all be zeros, but both sides should be symmetric. Yes. Hopefully that makes sense. So are there any like major questions, or did I cover this like good enough for everyone to understand?
Yeah, I just assume when it's heading in the direction, it's going to be connected, right?
Yes. Yeah. So now we have incidents, and this is a similar concept. You don't really have to worry about undirected and directed for incidents since you're just looking at edges as much. But essentially for our incidents, what I'm going to have to do is I'm going to have to label all of the edges. So we might have this is edge 1. This is edge 2. Edge 3. Wait, what? Say again?
Lines like EA, and then you have a line overhead. You can
Yeah.
the lines based on geometric. This is geometric.
Yeah. So anyways. So then we're going to have E4, which would be this edge right here. Sorry, this is a little bit hard to see. I've come to the realization. It's a little bit difficult, but we have E1, 2, 3, 4, and then E5 is right here. Now the question is, would you guys rather me do this complicated one, or would you rather have me do a simpler one so it's just like easier to see? I don't really care, but just which one would you guys rather have me do? Yeah, that way it's just like easier to tell, because this picture is like a little bit Like it's hard to tell, like, is this edge 2 or is this edge 2, you know, stuff like that. So I'll make a simpler one real quick. Let's see. So let's say we have this direct, or let's say we have this, 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 and this. And we just had. Okay, that's pretty simple, right? So let's say edge 1, edge 2, edge 3. And let's just say this is like vertex A, vertex B, C, and vertex D, right? Now to make a list, it's going to be pretty simple. However, now instead of, because we're doing this with incidents, now if you guys remember, I actually did go over the definition of incidents earlier. It is right here, right? Incidents is basically, you're looking at the edges. Like if an edge is incident to a vertex, it means that that edge comes off of that vertex, right? So when we're looking at incidents, we're looking at which edges basically are connected to which vertices. So I'll go back to red and I'll write down our, let's see, all of our vertices are A, B, C, D. And this is going to be an incidence list. So for A, which edges are connected, or which edges are connected to A, are connecting A, rather. If we look at this picture right here. E1, yes.
So you just write, so for the incidence list and I send the incidence matrix, you just write down. They just,
Yep.
yeah.
And for B, what about B? B is a little bit more complicated, isn't it? Yeah, E and E1, right?
And
Yeah. So E1, E2.
incidence can't have direction, though, right?
Right, yeah, don't worry about direction for incidents. There was no direction or anything mentioned in any of the online slides or anything, so I'm assuming that we won't have to worry about direction for this. How about C? C, it would just be E2, right? Yes. So now if we were to do the same thing and we were to make this into a matrices, once again, I'm going to start by labeling A, B, C, D. However, now I'm going to list the edges up here, E1, E2, and E3. And I'll make my little fancy matrices symbols. Now is A part of E1? Yes, but that's all it's part of. So it's going to be 0, 0. B is part of all 3. C is part of just E2. And D is E3, right? So does that make sense, guys? Because we're about to get into another topic that uses, well, actually more uses adjacency matrices, but we're about to get into another topic where we're going to be using adjacency matrices to prove something. So if this doesn't make sense, we're like, we gotta make sure it makes sense. But if it makes sense, we'll move on. What if there are, sorry, I was just looking at questions. Hubert, I will go through at the end because like I haven't been answering questions. So I'll go through at the end and like basically answer all your questions after like I finish everything. Does that make sense? Because like I just see like all of them. Does it matter if we put edges on left or top right? I don't think it should really matter, no, but I would just say like in all the examples I've seen, the vertices are just always on the left and the edges are always on the top. So like, no, it doesn't matter, or at least it shouldn't, but every single example I've seen has been in this format here. So I would just do this format. Okay, so now we're going to go over isomorphism, which is probably the most complicated part of graphs. But once you start understanding like how it's kind of like a puzzle, I don't know, it's like a jigsaw puzzle with graphs. Okay, so first of all, in order to be for two graphs, what is isomorphism? It's basically saying that two graphs can be mapped so that one is logically equivalent to the other. Okay, now the thing about isomorphism, there are these things, these principles that you must have true in order for something to be isomorphic. So if we get like a test question or something, and it's like, are these things isomorphic? And you notice that one of these principles is not true, the answer is just no. Okay. So first of all, the number of vertices, the number of edges, and the degrees of the vertices must all be the same. That means you must have same number of vertices, same number of edges, and you must be able to look at the vertices and be able to pair them to a number of edges the same way. Okay. Once again, I said that already, that you can map one graph to another, and we know that two isomorphic graphs that they will have a bijection. Okay, that means that for every part of one graph, it's all one to one and onto, basically. Yeah. So now, let's see. Are these two graphs isomorphic? How many vertices do they have? 5. How many edges do they have? Well, if I do the star real quick, it's a little hard to see, but 1, 2, 3, 4, 5, right? They have 5 and 5, okay? But that's not enough to decide that these two graphs are isomorphic. We can't just look at the number of edges and the number of vertices and decide, oh yes, clearly these are isomorphic. What we need to do technically to prove it, once again, not really, but technically to prove that these are isomorphic, is we have to go back to adjacency matrices, okay? So the first thing I'm going to do is I'm going to take one graph. It doesn't matter which graph you start with, just any graph. I'm just going to start with the one on the left because why not? And I'm going to make that adjacency matrix, okay? So I'm going to do this really quick that way, because like I already made this one previously. So I'm just going to go through it like real quick just so that we save time. So A, B, C, D, E, A, B, C, D, E. Okay, so A is not connected to itself, and we know that none of these are going to be. And A is connected to E and C. B is connected to D and E. C is connected to A and D. And then D is connected to C and B. And then finally, E is connected to B and A. If you guys notice I like make a mistake, let me know, just so I don't continue the problem further while like making a mistake. I don't want to like accidentally do that and then have it like mess up everything in the end. But anyways, so then after that, we're going to look at this graph. Basically, what we're going to try to do is we're going to start with any vertex of this graph, right? And we're going to try to create a mapping so that it makes the same adjacency matrix, okay? Meaning this adjacency matrix must be the same. So I'm going to start with F, okay? Now it has to be the same thing, right? In order to be the same thing, that means we're going to have the same first row, obviously. In fact, all the rows will have to be the same. So I'm going to write the first row here. 0, 0, 1, 0, 1. Okay. Now, what this is going to show, I'm just going to get my notes open, just because I do have some notes over here. But what this is going to show is essentially, we have this one here and we have this one here. Now, what do these ones mean? This means that they're connected, right, to something. Now, which one is F connected to? H and G. So what that means is that I know that H and G have to be above those ones, right? Now we're going to continue. So we have H here, right? And we know that if we go to this third column, it's kind of like C, right? We know that it's going to be 1, 0, 0, 1, 0. Okay, so we know that H is connected to F, right? But what is H also connected to? I, right? So that means if we go down this way, we can see now that I must be right here. Do you guys see that? Because I must be right there, because if it's not right there, then that means that we aren't going to have the correct mapping. And basically that means that H would not be connected to I. But we know that H is connected to I because we can see it in the graph here. So we're going to put I right there. Now, after that, we're going to basically continue the same logic with G. So G, we can see in this is kind of like the same position as E, right? We know it's 1, 1, 0, 0, 0. And which other is the one that G is connected to? So G we know is connected to F, but it's also connected to J, right? So J goes right here. Okay. So now what we can do, which is the one, we can go to this row, we can go to the B row, and we can copy this, right? Once again, it's still the same, 0, 0, 0, and then it's 1, 1. Now let's look at J. Once again, we know that J is connected to G, but what other is it connected to? It's connected to I. Now notice I is in the same spot right here and right here. Do you guys see that? So I is in the fourth spot down here. I is in the fourth spot up here. That is on purpose. So that means that basically what's going to happen is you'll see that basically all of the values up here and all the values down here will end up being the same. So what we're going to say now is that if we copy this I down with this D, we're going to get 0, 1, 1, 0, 0. Now, once again, we know that I is connected to J. What is the other one that I is connected to? It is H. So we can put H right here. We can then say that H is going to be the same as C over here, which is going to be 1, 0, 0, 1, 0. So what is the other one that H is connected to that is not I? That's going to be F. Once again, it's the same, it matches up. Keep that in mind when you're on an exam. If you just know that it matches up, you can do this very quickly. Now what we can say is we know that I here is going to match this D row. So this I row is the fourth row, D row is the fourth row. So we're going to go 0, 1, 1, 0, 0. For I, it's connected to H. What else is it connected to? It is connected to J. Once again, you can see that J matches up. And then finally, we can say that for this, let's see, what do we want? We can put 1, 1 here. Now, which vertex is connected to both F and J? We have F and J, that's going to be G. Right. So now, notice we have a matrix. Notice this matrix is the exact same as the other matrix, but just with the different values of this graph instead of this graph, right? So what we learn here is that if we look at where these match up, basically these two graphs are really the same graph. They just kind of switch positions a little bit. It's really that A maps to F, B maps to J, C maps to H, D maps to I, and E maps to G. That is technically, once again, how you quote unquote prove this. You can also just like look at them and like move them around and realize that if you kind of untangled the first graph, it would turn into the second graph. That is a valid way, but if they tell us to show work, I think that showing the matrix work would be the proper way to do it, to get full points, if that makes sense. That's the end of the slideshow. So we're basically done with the required part of the review session. I'll just start answering questions now. I am going to stop the recording. That way the recording doesn't get too long, but I'll stay here to answer questions. And obviously, if you guys have any other questions, you can feel free to message me on Discord. Thank you everyone for coming. And I appreciate everyone in person. And I'll peace, see you guys. Yeah, I got you. Hold up.